once we have trained the model, we can save it for the future use. For example, we can use this function to save the whole model to this file. And this model will be saved on your computer. So basically, this saves the model, saves the width estimates. And later on, if you needed to use this model, you can reload the model into R using this function. This is particularly useful. The reason is it would take a lot of time to train your model. And if you need to use your model for the future prediction, you don't want to retrain the model again. Once you save the model and you load the model, and then you can do the prediction using a model as you are using a model you just trained in R, like this. So a lot of large language models like ChatGPT, they first train the model and then save the coefficient. So when you need to use that, you just input your data, it will give you the output of the results. So far, I have showed you example on the use of continuous data and the text data in neural network analysis. Nextly, I will briefly discuss an example for image data analysis. So basically, I will show you how to apply deep learning models to image data. The data used here is this data set. So the data set included 20,000 scatter plots and the correlations of each scatter plot. So as we know, using a scatter plot, we can look at the correlation or association between two variables. For example, here, you may have a correlation 0.7, and you may also have a negative correlation like this, maybe negative 0.4. So basically, we have this plot information and we have the correlation. So that's the data set. We split our data into two parts. One is the training data, another is the validation data. For the training data, there are 10,000 scatter plots. For the validation data, there are 2,000 scatter plots. And if you take a look at the data set, we also have the training matrix X, training matrix Y. So this is the correlation value, and this is the scatter plot. We cannot directly save the figures. We have to save the scatter plots in the digital format, which means we convert the scatter plot into data. So for the training data set is 10,000 times 127 times 127 matrix. This 100 times 27 times 127 matrix is constructed in this way. So suppose this is a scatter plot. So we divide this scatter plot into pixels. 127. So this one would be 1, 1. So it's 1 pixel. Then I save the information of that pixel here. So therefore, it will need a 127 times 127 matrix to save information for one scatter plot. Overall, this is a three-dimensional matrix. And similar for the validation data. I'm going to use the R package image R to show you the basic information of the plot. So this would read the data. This would read the data change the data into the image format and plot that. So this is the plot of the first scatter plot in this data set, represented by the values here. Okay. So that's basically this part. So the matrix sees the information here. The first correlation here is negative 0.457. Then for another plot, scatter plot, the eighth one, so this is the plot, and this gives you the correlation negative 0.765. Okay, so that's the only data in my data set. And the purpose of this example is to build a neural network model, so we can feed a scatter plot to the neural network model, so it will output the correlation of the scatter plot. So this is more like if I give you a scatter plot and ask you how observe it, and then I will ask you what's the correlation what's the correlation is represented in this scatter plot? You will tell me negative 0.7. In this algorithm, if we feed this figure to the algorithm, it will output something close to negative 0.7. So that's the idea. To analyze this scatter plot data, we are going to use a convolutional neural network model. The convolutional neural network model in keras will take the input as a multiple channel image. So which means oftentimes we have a color images. Color images have 3 different prime colors. That's RGB, red, green, and blue. Here I only have 1 channel, but I need to convert my data into that format that can be used in keras. So keras oftentimes use a format like this. It's a 4-dimensional matrix. So I add this dimension 1 here. For the color image, this should be 3, but here I only have 1. And I change all my data matrix into this format. So this is for the training data, and this is for the validation data. Now let's build the convolutional neural network model. Convolutional neural network model is very effective in classifying images or classifying visual objects. This CNN model basically mimic how human process images, how human recognize specific objects. Okay. And for example, when we look at an image, if we need to decide where is something in it, for example, if we want to know whether there's a face in a photo or in a plot, intuitively, like a human will do that in this way. We first look at the figure, we identify the most important features. For example, we may identify the ears, we may identify eyes and the nose, right? So those features, we put them together, they give us the shape of a face, and then we'll see there's a face. Right? So the convolutional neural networks basically want to identify those features in the plot, and then or in figures, and then we use that to recognize objects in an image or in a figure. Particularly, a convolutional neural network using at a convolutional layer in the neural network model. This convolution layer can be estimated or can be predefined. And if we don't know the information about the convolution layer, and then we can estimate that. The convolutional layer actually uses something called the convolutional filters to amplify the information in an image or in a plot. The filter is, there should be a filter. It's actually a numerical matrix. You can think about like the simplest filter could be like a matrix of 0 and 1s. Right? Ones means there's the feature we are looking at there. 0 means no. And then we can just multiply this filter to the data we have. So if there's a feature there, and then it will be, the value will be there. If there's no feature there, it becomes 0. So in this case, it's kind of like a highlight the information we have in that image. So this is an illustration of how this convolutional neural net works. So we have the input, and if we have a color image, we have RBG. We have RBG data, and then we use a convolution layer. We change that to be a new layer with all those like features extracted from here. And in use CNN, we oftentimes will combine a pooling stage or the pooling layer. Pooling layer, which means we want to combine the information. For example, we combine those part of the information into one, reduce the dimension of the data. And then we can again add another convolution layer, and then we keep doing that. Eventually, we can use the typical neural network layers in the model. How do we specify the model? We can again use the sequential method, but now the first layer will be a convolutional layer. This is a 2D plot, so we just use 2D function. And the filter here means the number of features we want to extract. Here I use 32 filters. I want to estimate the 32 filters. Each filter will have its size. We call it the kernel size. So it's the 3 by 3 here. 3 by 3 means I would use a filter like this, 3 by 3 matrix. And here I assume I know the 0 and 1, but in my model here, I actually estimate those values. So maybe this estimated value may be 0.2. This will be 2.1 value here. So those values are decided by the algorithm, by the estimation process. Pattern equal to same. So this means whether I want to fill in the data into my matrix or not. Remember, like, so this is my onion data, and if I move the filter through here, and eventually I will move out here, right? Pattern means like I want to keep whether I want to keep the same I want to keep the same dimension of the data or not, right? This means after filtering, I still have the 127 times 127 dimension. And then I use the activity function, is ReLU. The input shape. Here the input shape is, we have 3 numbers, 127, 127, and 1. The reason is because my data format is here, right? So the shape basically all the dimensions here. The first dimension we don't need input because we need to specify the batch size. Then I add a layer, pooling layer. The pooling layer basically, now I have 127. So this is 1 and 2, and this 1 and 2. So which means for each of these 2 by 2 matrix, I combine it into 1. There's different ways to combine them. One way to do that is, for example, if it's 0, 1, and 0, 0, I just use 1, right, as a combined value. Or you can use average. So I can combine those. So each of these combined to be 1 value. I can reduce the dimension from 127 times 127 to 63 times 63 from 1 pooling layer here. And then I add another convolution layer. So this is more like the first layer, maybe like I identify the most basic information like years, like nodes. I identify the features about years and the nodes and as, right? And then the second convolution layer basically means now, okay, I want to combine the as and nodes together to form a face. So that's one way to think about that. Now I want to have 64 convolutional filters. The kernel size again is 3 by 3. Padding equal to same. Activation is very low. And then I put the data together. And then I add another layer. I have 128 filters. After doing all of this together, I would have a new output. The new output would be 15 times 15 times 128. So 128 is the final number of features I get from the plot. 25 is after putting the data together. Okay. Now later on, I want to fit neural network models to these features again. So I'll first change, because this is the matrix format, right? I want to change this to be a very big vector. How to do that? If I have a matrix look like this, right? So I can stack each column together, right? So this become a long vector. Now I have multiple of those matrices, and then I stack the matrix together. Okay, so that's what the layer flattening does. It flattens the data from a matrix to be a vector. So in this case, I have a vector size look like this. So 28,800 times 1. You may think about this as my input. Now I have input like this. Those are all hidden layers. Okay. Then I put my neural network model. In my neural network model, the first layer I have 128 nodes. So this is first layer, 128 nodes. Okay. Then I have one output just. For this hidden layer, I use the activation function reload. For the last one, the output layer, I use the linear activation function. The reason I do that is I just treat the correlations as continuous data. So I just have 1. So which means for each input of the plot, I have one predicted value. If I know the width here, if I know the convolutional filters in the model. So overall, this specifies my model. Clearly, this model is much more complex than the model we used earlier. So this gives you the basic information about this neural network CNN model. So the first convolution layer, there are 320 parameters. The second one have this number of parameters. Then I have this number of parameters. And for the first hidden layer 1, we have this amount of parameters. The reason is this value multiplied by 128, right? Plus 128. So this gives the total number of parameters in this hidden layer. And in the output layer, I have 129 parameters. So in total, I have more than 3 million parameters. And this you consider not a very complex model. For the ChatGPT, for the large language model, it involves multiple billion number of parameters. And then I will compare my model by specifying the loss function, optimizer, and also the evaluation matrix. I first ran my model with 10 epochs, and I found if I use 8 epochs, it would give me the good results. So therefore, I rerun my model with 8 epochs. So this is my training data for the input and output. And for the validation purpose, I set validation split equal to 0.2. So which means among those 10,000 scatter plots, 8,000 of the plots were used for training, and 2,000 were used for validation purpose. Now we have the model. We want to see how well the model works. So we can apply the model to the test data. First, I made the prediction. So this is the input scatter plot. Okay, so I got my prediction. And then I plot the predicted correlation with the observed correlation. So this is a predicted correlation, and this is the observed correlation. Here I use the training data. I first look at the prediction for the training data. So you can see it's almost a straight line here, which means the prediction was very good. Certainly that's the case because for the training data, we oftentimes would overfit the data. But we want to know how well it works for the test data. Okay, so the test data is include the scatter plot we didn't use in estimating the model. Okay. So this predicted value for the text data. So this is the observed value for the test data. So this is a scatter plot. And again, for this test data, the model still works very well. So which means we can actually generalize the CNN model to the new data here. And I also calculate the correlation between the observed data and the predicted data. The correlation is almost 1. So which means, again, it performed very well in this particular example. So notice that now I have a scatter plot. And you may be wondering, how about I asked the program to I asked the model to tell me what's the correlation of this scatter plot here. So that's the idea, right? So we build a model to predict the correlation, now we have a new scatter plot. Can it guess the correlation correctly? Okay, now we can try this out. First of all, I want to save my scatter plot into a file on my computer. So that's the typical data you would have in practice. In practice, you may have a figure that's saved on your computer, or somebody give you a figure. For example, in object recognition, you may have a photo taken somewhere, and you want to recognize what kind of objects in it. So you already have an image file instead on your computer. So that's why I did it. I did this here. I first save the scatter plot to a figure. So the rest is actually the way to do the image analysis. I first load my figure into R. Right? So it tells me my figure is 480 times 480 matrix. It also has three channels in my data, but I know like my scatter plot is a black and white plot. So I first change that to be a one-dimensional data. I change this to be 1. Okay. So this is 480. But remember, in our model, our input is 127 times 100 times 27 times 1. Right? So we cannot directly input this data into our neural network model because the size of the data is different from the data we use to train our model. So the first thing I'm going to do is I want to resize this figure. Resize this figure means I want to make this smaller to be 127 to 127. And in R, we can just use the function resize to do it. Then I don't want to take out just one dimension of data because I don't have colors on my data set. So now I have a test data like this that is the same, that has the same dimension as the data I use to train my model. Okay, and then we can do a prediction. So I use a prediction test data and give me a correlation point 5.2. The correlation point 5.2 is not that good. The reason is because when we calculate the correlation, actually is 0.996. So which means the prediction is not accuracy. Why is the case? The reason is because when I save my scatter plot, it saves everything here, which means it saves the text here, saves the numbers here, it also saves the box here. But when I train my model using the plot, I actually only include this part. So which means it only has the dots here. It does not have the outside box. It does not have x-axis and y-axis. Right? So I wonder whether I can actually make the prediction better if I remove the outside box from this scatter plot. So that is what I'm going to do here. So I basically crop my figure by remove the box outside of the points of the scatters in my plot. Okay, and then notice that this is what I have. I only have this. Then I resize my data to have 127 rows and 127 columns. And then with that, I conduct a prediction. The prediction give me a value point of 1.028. And certainly it does not make sense because the correlation cannot be greater than 1. But it's much more closer to 0.99 we calculated from our data. Right? The reason it gives us a value 1.02 is because we treat the correlation as any conjecture data. We didn't fix it into the interval 0 and 1. If you want to get a prediction that always in the interval 0 and 1, you can change the activation function here. For example, you can use a sigmoid active function. We know that it changes every value to be the interval of 0 and 1. So after the workshop, you can practice this by changing this activation function to this one. And then you can make a prediction for this scatter plot. Currently, there are also better algorithms to do image process. So CNN is just one of the very widely used algorithm that are also accurate. Finally, I will give you a very brief introduction to recurrent neural network models. In our teaching evaluating data, we have analyzed data based on the individual words. In our data analysis, we basically ignore the order of the words. So this method is actually called the bag of words method. But as we know, in writing, the words actually have a specific order. For example, if we look at this, for the teaching evaluation data, we want to say for teaching the evaluation data or for teaching evaluation the data. That doesn't make sense. Right? In this case, intuitively, if we take into consideration the order of the words in the data, maybe we can get better results. It's not necessarily so, but sometimes when we get better results, or intuitively, we should get better results. Okay. The network models we talked about so far includes the model for the active data and for the image data. We didn't consider the order at all. So which means those networks has no memory. It does not remember information previously. To model the order of the data or the order of the words, we can use recurrent neural network models. And this model is particularly useful, for example, for time series data. If you want to predict the stock market price, this model would work much better than the network analysis that didn't take into consideration of the order of the data. So basically, for recurrent neural network models or RNN, the input from the previous time can be used as the input of the output from the previous time can be used as the input of the next time. For example, this is maybe like a time 1. So this is the input with have a hidden layer, and then we have output, or we have like you can think about you have a middle layer, and then this output A1 can be further used to predict the output at the second time. Now let's model the text data again. In this time, we use the recurrent neural network. To use the recurrent neural network model, again, we need to reformat our data first. we should have a different data format than the format we used earlier. Here we still keep the same number of tokens, but add the option output sequence length equal to 100. So this basically means I will keep like at most 100 words in my data set, but I will also have the sequence in my data. So this part is the same. But when we look at our data set now looks like this. So we have a shape like 100 columns. And in these 100 columns, so this number, not 0 and 1 anymore, but is the index of the words in the matrix. Remember, we have total number of words like this. I can have the here maybe test here. So each of these can have a value, for example, 0, 1, 2, 3 to 3,600. Right? So basically, this number represents the index of those words in this vector. Okay. If we take a look at the one text. So this gives us all the index of the words in this text. Okay, and given the index, we can reconstruct the comments, right? Because we just replace the numbers with the words in this vector or in this list. So this is how we reconstruct the text. Okay, here. Notice the unknown means like the words is not in that list. Maybe it didn't appear 6 times in the original data, so we don't have that word in that list. We can now also break the data into training data, validation data, and the test data. Now we specify the model. In using the RNA, oftentimes we do something called word embedding. The idea of the word embedding is to reduce the dimension of the data. And remember, like originally, we have this amount of words in our data set, right? And then we have this 10,000 text. This is a big matrix. Use the word embedding. We want to embed this data to be a lower dimension data. For example, we may change this to be a 10,000 times 128 dimension. In this word embedding, we basically combine similar words together. So this is more like the principal component data analysis. So basically, we do word embedding. So our input dimension is the number of words, and our output dimension is 128. Okay. With this word embedding, so the input shape for the RNA will become 128 instead of 3,000. In RNA, we can have different recurrent layers. So one popular RNA is called long-term and short-term memory recurrent neural network. So in this long-term and short-term memory methods, we can specify a number of hidden nodes, 32. And we also use the bidirectional function here. The bidirectional means when we fit the model, not only like the words here predict is related to next word, we also consider when we consider this, we also consider this can go back. So which means the previous word also depends the words next. So we can look at both directions in our model. So that's what we did here. And again, we can use we can drop out some ways to simplify the parameter estimation. The output layer here again has 9 units. The reason is because again we treat the each value as one category. If you already know your word embedding, you can use existing word embedding method. So in that case, you don't need to estimate that many parameters. But here, I want to estimate my word embedding. So in this embedding layer, I need to estimate this number of parameters. And then in my RNA layer, I need to estimate this number of parameters. In the output layer, this number of parameters. So in total, I estimated about 500,000 unknown parameters in this RNA model. I again started with 20 epochs. I ran the data analysis, and then I found if I use 12 epochs, I would get a good results. So the optimization method is set as the same as in the previous analysis. The batch size here I use 200, which means each time I input 200 text to my data. So this is a refit of the model with 12 epochs. Again, make sure you set the random seed so that you get the same results each time. Let's take a look at the prediction accuracy here. Now I achieve accuracy is about 61% or 60%. Earlier, when we conduct the data analysis using a regular neural network model, I have the prediction accuracy about 62%. Now I have 60%, which means even I consider the order of the words, it didn't perform as better as well as the simpler model. And again, it suggested the more complex model may not give you better performance. And actually, in text analysis, people found that if you use the backgrounds and the regular neural network model, it can perform much better. But it's not always this case. It depends on the data you have. It depends on a lot of many other factors for a model to perform best among a set of models. Just in this case, we found that this model didn't perform as well as a regular neural network model. But if you have a different data set or you have a different job or task, you may find the recurrent neural network model can perform much better than regular neural network model. So that's all I want to show you in this workshop. To summarize, I have used the psychological data set, the active data, to show you the whole process of doing neural network analysis or deep learning analysis. After that, I also showed you how to build a neural network model for the analysis of text data. Initially, I used the regular neural network model with, I believe, 2 layers. Then I also showed you how to do this using a recurrent neural network model. And then I also showed you how to use convolutional neural network model to process image data. So basically, we predict the correlation of the scatter plot. Because of the time limit, I cannot go to very details of each method, but hopefully through this workshop, you have learned the basic knowledge to do neural network analysis. I hope after the workshop, you can run the code in the workshop and try to understand the code. And then you can try to apply the same model to your own data. And hopefully in the future, you will use the neural network models in your own data analysis. And thank you again for taking this workshop. And if you have any questions, feel free to contact me.